Okay, so I wrote these weird looking words here, Zermelo-Frankel / choice, etc. What on earth does that mean? So I told you we're going to be informal about set theory. So we're not going to describe it in an axiomatic way. What do I mean by axiomatic way? Well, you might remember from studying geometry, Euclidean geometry, go back to high school, and there were these certain statements that were called, they might have been called axioms or they might have been called postulates, depending on how it was taught. And, for example, you might remember that there was some controversy about the fifth postulate in Euclidean geometry, which says that if you have a line and then you have a point that's not on the line and there's only one line you can draw through that point that's parallel to the first line. So those are axioms, or sometimes they're called postulates. And so what an axiom is it's something you assume is true. It's like you think that it's self-evident or something. You know how in the Declaration of Independence it says, we hold these truths to be self-evident, that all men are created equal and so on? Well, that's what you're doing when you set up an axiomatic system. You're saying, we hold these truths to be self-evident, that well, these things are obviously true, so we're going to base the rest of our logical system on this. And so the same thing can be done for set theory. And of course, there's more than one way to do it because you have to decide what your axioms or your postulates are. So the most popular or most commonly used version of set theory today is this thing called Zermelo-Frankel set theory. And so this thing, Zermelo-Frankel, and usually people say, so you see ZFC, and the C stands for the choice here, and I'll tell you what the choice means in a second. But what this consists of is this consists of 9 axioms. So if you think it was a nuisance to remember the axioms of Euclidean geometry, well, this is worse, and so you should be very grateful that we're not doing it this way. We're not, actually approaching set theory in this formal sort of way. Now, these axioms are statements that seem so obvious that you would forget them just because they seem so obvious. You know how sometimes it's hard to remember something when it seems like it should just be absolutely clear that it's true. And for instance, they say things like, if 2 sets have the same elements, then they are the same set. That would be an example of one of the axioms there. So, e.g., if 2 sets, which I could call S1, and that doesn't look like a very nice S, does it? If 2 sets, S1 and S2, have the same elements, then they are the same set. Now this one, the reason I mentioned this axiom in particular, because it's actually worth clearing up a potential point of confusion. You remember that first example that I wrote there where I said, let's talk about a set that has 3 elements and they happen to be 1, 2, and 3. Well, what if I wrote a set that had elements 2, 1, and 3? So here's my S1 and here's my S2. So in what sense are these 2 things the same, and in what sense are they different? They're different as lists. So if you think about a list as being something that has an order to it, because if you make a shopping list, you have the thing at the top of the list, and then second, and third, and fourth, and so on. Well, it would be a different list if you rearranged it, but it might have the same items on it. So as lists or as sequences, that would be another way to say it, these are not the same. But as sets, they are the same. And so what does that mean? What does that really mean? It means that when we talk about sets, all we care about is what elements are there. We don't care about any other structure that may be present. For instance, we don't care about, like, these number systems here that I talked about. Remember how I told you that the natural numbers, we like to include 0 because it's an additive identity. Well, addition is something that is additional, no pun intended, to the set structure. So the set structure of the natural numbers only cares about what elements are there. It doesn't care about addition. So then, of course, you could argue, well, in that case, why do we care about putting in 0? Well, even if we only think about the natural numbers as a set, of course, that's not all we're going to do with natural numbers. Eventually, we will add them and subtract them and multiply them and so on. But the point is that when we're just talking about sets, we do not care what order things are in. We do not care about adding things. We do not care about subtracting or multiplying or any operations. We don't care about relations like less than or greater than, any of that stuff. We don't care about it. All we care about is what elements are there. So this, we can put in equals between these. These are equal as sets. So if we think about these things as sets, which is what we are doing when we write them this way, then all we care about is what elements are there. Two sets are the same if they have the same elements. Now there's 8 other axioms, and then there's also this additional axiom which is called axiom of choice. So Zermelo-Fraenkel, so ZF, the Z and the F, Zermelo-Fraenkel, that gives you 9 axioms, and then you have one more axiom, and this is axiom of choice. And it says another thing that you would think is obviously true. It has something to do with infinite sets, and it says that, okay, if I have a bunch of infinite sets, then I'm allowed to take like one element out of each one of these. And you'd be like, well, why couldn't I do it? But it's complicated. This kind of axiomatic set theory is complicated. It can become complicated. So I'm just peeling back the edges of it just a very little bit for you to see, and it's partly just for your general education if you want to like look this up on Wikipedia or something like that, but it's also partly so you'll be grateful that we aren't developing this in an axiomatic way, because that would be a nuisance. It would be hard to remember. So we're going to be aware that this is here, that this can be done and has been done and so on, but then we're going to just kind of leave it there. We're not going to mess with the details of it anymore. Okay, so let's go back to some more practical matters here. And in particular, we want to talk about different ways in which we can specify that an element belongs to a particular set. So that's this ways to specify membership. So the membership there means membership of an element in a set. Now, one way is just to say that a particular element is in a particular set. So I could say the element A, I'm just going to say A, belongs to the set S. That's one way that I could specify set membership, and that's a very explicit way of doing it. It makes it perfectly clear what's happening. Now, it's a nuisance to say all this and to write all this. So what do we do instead? Well, we write a shorter statement, symbolic statement, and that's this statement here. So we write A, and then we write this funny looking symbol here. It kind of looks like an E. So you can think, so this is, we can call this element symbol. That's what we can call this. And you can think of it kind of as an E, like, it kind of looks like an E. They kind of look like the same thing. And so what the element symbol, and then so of course we put the set over here. So what is this saying? Well, the thing that's over on this side is some element. The thing that's over on this side is some set. And so what the element symbol does is it just links those two together. It says that this element belongs to, so another way you can think of it, the belongs to part, that's what's being said by this. That's what the element symbol is saying. So this bit here, the element A, well, all we need to really say is A. And this part over here, the set S, well, all we really need to say is S. And then the belongs to is that element symbol there. So that's one way that we can say it. Now, remember how, when I was telling you about, let's use this little set here as an example of what we were doing before. So, for instance, the element 2 is an element of the set 1, 2, 3. That would be an example. Now, the number 4 is not. Now, how do we write is not? We write the element symbol, and then we write a slash through it that says is not an element of 1, 2, 3. So this says is not an element of, and this says, of course, is an element of. And then we could do similar examples using some of our number systems. For example, we could say, well, 17 is an element of the natural numbers, because it is. Or we could say 0 is an element of the natural numbers. And you remember how I said before that we like to include 0 in the natural numbers because it's an additive identity. -2 is not it's not an element of the natural numbers. Now, I stumbled when I was speaking there. I said, is not in. You heard me say that? That's something that people do. They say that if 17 is an element of n, then they'll shorten that and they'll just say 17 is in n. Or 0 is in. So you're thinking about is in, and so of course, you know, what would happen over here? I'd have 0, 1, and 2, and then I go on for a while, and then eventually I hit the 17, and then I keep going on. So if it's in that list there, then it's an element of. So that's why people say that an element is in a set rather than that an element belongs to a set, but it means the same thing. Now, why wasn't the -2 in here? Well, because this starts at 0 and then it counts up. It doesn't include the -2. However, I could say that -2 is an element of the integers, right? Because the integers, remember, the integers included all the negative ones too. So -2, -1, 0, and then, you know, this keeps on going that way. So -2 is an element of the integers. It is in the integers. It belongs to the integers. Okay, so that's one way that we can tell that a element is in a particular set by just saying it is and using this statement here. Now another way which we've been using, and I just realized that you probably can't see my little colons here, list and rule here. And I guess there's another one over here, isn't there? And there's a dot, dot, dot over here, which you probably can't see because of the glare. Oh well, it doesn't matter. Something that we've been doing, so a second way to specify membership of an element or elements in a set is to just list them all, and that's what we did at the beginning. If you're given a set, some set is just a list of things, and it could be anything. It could be a star, and it could be like a smiley face, and it could be I don't know, what else should I draw? Little triangle, then you can tell which elements are in the set if you have them all listed just by looking and seeing if something's in the list. So that's a very simple thing that we've been doing. Now another thing that you can do is you can specify some sort of rule that an element has to satisfy in order to be included in a set. And so that's what I've kind of done here. Let me recopy this here. So suppose my set is all even numbers. Now another way to write all the even numbers would be to, well, it depends on which numbers you're considering to begin with. For example, if you're only considering the natural numbers, then you would say, well, my even numbers are 0, 2, 4, 6, and so on this way. Whereas, so this is even numbers, this is in the natural numbers. Whereas if I was thinking about all the integers, then I would have to include more, right? I'd have to include, so dot, 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 comma, say -4, -2, 0, 2, 4, comma, dot, dot, dot. And this is if I'm thinking about all of the even numbers in Z, in the integers. Now, what this brings to mind, so you might say, well, what's the answer? Is it this one or is it that one? Which is it? Have I not specified carefully enough just by writing this even numbers? Well, so later we're going to talk about this thing called universal set. So this is later. I may be writing up here where the glare is, but later we're talking about universal set. And the idea of a universal set is that you take a set which is big enough to include all the numbers you happen to care about, or not necessarily numbers, it could be anything, all the elements that you care about. And then every time you specify some sort of rule that elements have to follow, you're assuming that they belong to the universal set to begin with, and then your rule is narrowing it down further beyond that. So in this case, the universal set, and so we could call universal set U. In this case, the universal set would be the natural numbers. This is an equals sign written vertically, by the way. I'm allowed to do that. I can write equals vertically. And here is, in this case, the universal set would be the integers. So what you mean by even numbers depends on what numbers you're considering to begin with. Is it only the positive ones or does it include the negative ones? Well, you have to specify what your universal set is. What's the set that you're taking them out of to begin with? And then that tells you which ones you're allowed to take out and which ones you aren't. So you can specify a rule that way. And we just saw from that example that if you want people to understand what you're talking about, then your rule has to be pretty specific. It has to be sufficiently specific to give enough information to make it clear which elements you actually mean. Now there's this very useful and general method of representing a set using rules or conditions or criteria or however you want to say it on certain elements. And this is what's called set builder notation. So let me tell you a little bit about set builder notation. So I'm just going to copy this here. Set builder notation. And so this is a way, so this is a way to specify, well, I'll say a set rather than sets. Well, I guess I could say either, it doesn't matter. Way to specify a set using elements. Well, I mean, any set is represented in terms of elements, but I mean, I'm sort of taking like elements out of a universal set or something like that, a large collection of elements, and then I'm going to narrow it down. So using, let me say it this way, using a general collection of elements, and I could, if I wanted here, I could say universal set if I wanted to. General collection of elements. And so this would be universal set if I want to put it that way. And rules or criteria for membership. Okay, that sounds a little bit messy, right? Took me a little bit to write out there, so it sounds maybe a little bit, you might be a little bit iffy about whether you like this or not. Well, you should like it, and you'll see as we go along, I hope, why it's a convenient way to talk about sets. So this is what you do here. So you write S over here. So what you're doing over here is you're naming the set. So this is name of set. And then you open a brace here, which is what we're used to doing. And then you write some elements. Now, typically the way you write these elements is by specifying that they belong to a larger set or collection of elements here. So some elements, and then you're going to narrow it down by specifying some rules. So this is rules obeyed by these elements. Now, in this first example here, I wrote, let's just look at this first example here. So I wrote x, y, and oh, what did I do here? So I wrote x, y. Now, x comma y, what I meant is that both the x and the y are in the real numbers. I should have really put R2 here because it really means, R2, that means the plane. It means that both the x and the y belong to the real numbers. Let me clear this off here and I can explain this example a little bit better. Okay, so let's just copy this example here and think about it a little bit. So the set we're talking about is a set. Now, what do the elements look like? Well, all the elements look like an ordered pair R2, let me write it out and then I'll go into the details a little bit more. Okay, so first of all, this R2 thing. So this R2 means, what does it mean? It means the set of all ordered pairs of real numbers. That's what it means. So the real part here, the fact it's real, that's why there's the R there. And the fact that it's pairs, that's why there's the 2 there. For instance, if it were real triples, or triples of real numbers, it would be R3 instead of R2. Let me take these out. Now, how are you used to writing pairs of real numbers? Well, what you're used to doing is writing a plane. Think about the Euclidean plane. So you have an x and a y. And so any point here, so this is the x-axis. Let me actually write the words here. X-axis and the y-axis here. And then what any particular point here is you would write its coordinates as x and y, right? And so what is the x? Well, the x is here. That's the distance from the origin to that point on the x-axis. And then what is the y? Well, the y is this distance from the origin up to that point there. So it's an ordered pair, and we represent it by the Euclidean plane or the Cartesian plane or whatever you want to call it. So that's why we say R2. Now, if we want to be more formal, then we would write R2, or we would recognize that R2 is what's called the Cartesian product. So you see this little cross symbol there? That's not an X. That's like a times. It's like a times here. And this means Cartesian product. And Cartesian, it's the same word as you say Cartesian plane. You're used to Cartesian plane. And it comes from Descartes, who was instrumental in beginning to develop what's called analytic geometry, which is where you're doing geometry. I mean, the plane is kind of a geometric thing, right? And so when you're talking about coordinates in the plane, then you're assigning numbers to geometric things, and so that's where the analytic geometry sort of idea comes from. So that's what the R2 is. It's the Cartesian plane, and so an element of R2 is an ordered pair. But see, this S we're talking about here in this particular case is not the whole plane, because, I mean, if it were the whole plane, I'd save myself a whole lot of trouble, and I would just write S equals, so I'm writing a question mark here because this is not right. I'm just saying, if S was the whole plane, I would just write it that way and be done with it. I wouldn't have to write all that other stuff. So S is not the whole plane. So S is not the whole Cartesian plane. R2. You can say Euclidean plane too if you like, because it's Euclidean geometry works in the plane, whereas it wouldn't work in, like, on the sphere, for example, surface of the sphere, or in a hyperbolic space or something that has curvature. It wouldn't work in that context. But this S here, it's not the whole Cartesian plane, because the xy here, so the elements x, y have to satisfy the rule that y equals x. Now, why do they have to satisfy that rule? Well, just because that's the set I want to talk about. So that's the rule that I've specified. And if I want to talk about a particular set, then I can decide what set I want to talk about, and then I can specify a rule that will make the elements belong to that set. Now, it's useful to think geometrically about what does this set look like. And of course, it's very familiar. Here's the y-axis. Here's the x-axis. And the points x comma y such that y equals x are just all the points that live on this line. See, every point on here, like this might be the point 1 comma 1, for example. And this might be the point 2 comma 2, for example. So what have I done, and why would I need to do this? Well, if I want to talk about that line, as a set, I mean, suppose I come at it from a geometric perspective to begin with. And suppose I start out with the plane like this. And so here's the y-axis, and I keep on redrawing this picture, but it's just as well. Here's the x-axis, and then I'm talking about this line. And suppose I say, okay, well, I want to think of that line as a set. And so that means I want to specify what elements are in there. So I want to be able to say, what elements are there in this set? Well, I know every element here is certainly an ordered pair of real numbers, because everything in the plane is. So I know any element there is an ordered pair of real numbers. But not every ordered pair of real numbers will qualify. I mean, I have this one out over here, for example. That's not on the line. Now it's an ordered pair, it's represented by an ordered pair of real numbers because it's in the plane. Everything in the plane is. But it's not on the line. So how do I then go and say it's on the line? Well, so that's why I need this set builder notation here, because first of all I need to say like what kind of things are these elements to begin with, and what they are is they're ordered pairs. Okay, well they're ordered pairs. Ordered pairs of what? Well, ordered pairs of real numbers. So that's why I need this part. You know, this tells me ordered pairs of real numbers. Maybe I'm writing up there where there's the glare again, I'm not sure. Ordered pairs of real numbers, but that's not enough because not all of them qualify. I need to give a rule of qualification or membership, a criterion that these things have to satisfy to make sure that they're on the line. And what that is that's precisely the equation here, y equals x. So this is ordered pairs of real numbers such that, so that they're just the ones that are on the line. So this is just says on the line I was talking about to begin with, y equals x. So that gives you just a very brief description of this set builder notation method and how we might use it, and we'll see many more examples of this.